For almost all of human history, the night sky has guided us across continents, illuminating our path forward. The stars are as entwined with our civilization as are the land and the sea. But that sky is changing. While the stars, nebula, and supernova remnants are as brilliant as ever, few of us will ever get the chance to see them as they once were, even though all it would take to do so is a flick of a switch. I'm Alex McColgan and you're watching Astrum. Join me today as we explore how the night sky has changed in our own lifetimes and uncover the drastic effects that artificial light, both visible and invisible, has had on us, on crucial ecosystems, and on important scientific research. We will see how a well-intentioned green revolution made it worse, how we've put artificial constellations of our own into orbit, and how even the natural constellations themselves are changing. That's right, we're going to see how our sky will change in 1,000, 1 million, and even billions of years into the future. In the 1994 earthquake in Los Angeles, a large part of the city's electrical grid was knocked out in the early hours of January 17th, revealing the effects of decades of increased light pollution in an instant. So shocked were the residents by what they saw as they evacuated their homes that some looked up in awe of what had always been there, hidden by the city lights. One even phoned the observatory to ask what the giant silvery cloud was that they were seeing. Sadly, even the sky when you first looked at the stars as a child is not how it is now. From 2011 to 2022, the average light pollution increased by 10% a year, meaning it has more than doubled over that time. So let's travel to a dark sky location on a clear night, far away from the sky glow of towns and cities, and look up to understand what we've lost before we learn how we might get it back. There is a useful measure used to rate the quality of the night sky by eye called the Bortle scale, which ranges from 1 to 9. In a city under the brightest of skies, you may only be able to count 100 stars. This is a 9 on the Bortle scale. But as you travel away from the lights, the sky reveals more until it becomes nearly unrecognizable. As you drive out to the surrounding urban area, the night sky darkens to Bortle 7. Here on a clear night you might get to see a hint of the Orion Nebula, visible only as a diffuse looking star. Clouds under these skies will be very well lit. Once you're out past the city limits into the rural countryside, you're now under Bortle 3 skies, and much more is revealed. Messier objects 15, 4, 5 and 22, all star clusters, are now naked eye objects. Andromeda is clearly visible, and if you look carefully, you'll glimpse the Triangulum galaxy. These two galaxies at 2.5 to 2.7 million light years away are the furthest objects we can see with the naked eye. And what about that giant silvery cloud they saw in Los Angeles? That's our Milky Way, a diffuse band that arcs across the sky, which contains over 100 billion stars. Finally, after a few hours of driving, you're now under Bortle 1 skies, a true dark sky sight with a pristine view. When we set out from the city, you could only see 100 stars. Here, you will see thousands. It may even take you some time to notice the constellations that you thought you knew, lost as they are in the awesome detail of this dark sky. If you're lucky enough to live in the southern hemisphere, you'll be looking towards the galactic center, and you may even notice that it casts shadows onto the ground. My friends in the northern hemisphere, no need to be envious. Our fortunes will be reversed as we orbit to the opposite side of the galaxy in a mere 120 million years. Elements of the beautiful Orion complex are visible in both hemispheres, a 1,200 light-year wide star-forming region containing the Horsehead, Flame, and Orion nebulae, though binoculars are strongly advised. The closest object that is fully revealed in such a dark sky produces no light of its own: interplanetary dust. This dust is illuminated by the sun and forms a band known as the zodiacal light, which spans from the horizon to horizon, featuring a central focus called the Gegenschein, appearing directly opposite the sun's position over Virgo. Sadly, those of us who live in cities never experience a genuine night sky at all, and are effectively stuck in an artificial twilight. This can have unexpected effects on us as well as the night sky. So, how do a few light bulbs block out an entire galaxy? In a word, sky glow. Any light that is emitted upwards will pass through the atmosphere where it can be scattered in any direction. The light that is reflected back towards the ground to our eyes or telescopes is seen as sky glow, which has the effect of drastically reducing the signal-to-noise ratio of incoming light from space, affecting our ability to see it and to study it. You may have experienced something similar on a dark, foggy drive. Perhaps in an attempt to see more of the road, you've turned on your full beams. The slight upward angle of these lights reflects light up, illuminating the fog in front of you, which has the opposite effect of what you intended. It bleaches the field of view and obscures the road ahead. To make things worse, it's not just that the sky is now brighter. Tragically, our eyes are now also less able to see in the dark when we go outside. Human eyes have the incredible natural ability to detect brightness across a full 9 orders of magnitude. We are able to do this because we have 2 types of vision. The first is known as photopic vision, and it's the one you're using now. It's our daytime color vision recorded by our eye's cone cells. The second is scotopic vision, an ultra-sensitive monochrome night vision recorded by our eye's rod cells. It is this scotopic vision that allows us to see the faintest details in the night sky. Modern lighting is reducing our access to scotopic vision because, to the human eye, all light is not equal. In the past 10 to 15 years, a movement towards more energy-efficient LED lights has shifted the spectrum of light pollution from the orange hues of the sodium lamps to the blue-green frequencies of LEDs, which we are much more sensitive to. These blue-green frequencies slow down dark adaptation, or worse, can fully reverse it in minutes, which is why you'll often see astronomers and nighttime pilots using red lights or red goggles to ensure scotopic vision is maintained. To access full scotopic vision, we require a near absence of short frequency light for at least 30 minutes, and it can continue to improve for up to 2 hours. So, you may be wondering, if we are so sensitive to the blue frequencies of typical LED lights, why can't we use less of it and reduce overall light pollution? And you'd be right, we could. The reality is, though, that we don't. LEDs are so efficient compared to sodium and filament lights that we save energy and money even when they're run much brighter. So that's what we often do. We run them brighter because we all feel safer in a well-lit area, even if we are statistically no more likely to be the victim of crime. Our eyes also contain retinal cells that are not involved with seeing and instead help to regulate our body clock. These cells are particularly sensitive to shorter wavelengths too. So, artificial light, and LEDs in particular, don't just affect our ability to see the night sky. They affect us in other, more severe ways too. The disruption of our circadian rhythms by light disrupts the production of several key hormones, including melatonin. Incredibly, this can affect our body through a dramatic cascade that can lead to metabolic and mood disorders, and most severely, cancer. While for us humans there is at least some upside in extending the length of the day artificially, for the rest of nature there is almost nothing but downside. Lights interfere with the circadian rhythms of wildlife too. disrupting how and when they sleep, migrate, reproduce, hunt, and evolve. Almost every species studied to date is negatively affected by lighting, at the level of both the individual animals and their populations. Scientists have studied fishes, birds, amphibians, insects, invertebrates, ecosystems hundreds of meters down below the surface of the sea, and even trees. Deciduous trees, which regrow their leaves each year, can be tricked into maintaining their foliage all year round, causing stress that can eventually kill the tree. There are simple things we can do that manage that rare combination of saving us money and improving our health. The best, of course, is to turn off unwanted lights, particularly outdoor lighting and uplighting. When installing new or replacing new lights, look to install low power LEDs with low color temperature of say 3000 Kelvin instead of 5000 Kelvin. Well-designed lighting will have shielding to focus the light to where it needs to be and minimize excess light shone into the atmosphere. But away from ground-based artificial lights, we are now facing a significant increase of light pollution coming to us from space. On the 4th of October 1957, the Soviet Union launched Sputnik 1, the first satellite to venture into space. In the decades that followed, there was a steady increase in the number of active satellites, increasing by 30 a year on average in the 60 years to 2017. But from 2018 onwards, Elon Musk's SpaceX has been doing something unprecedented. Before we get to that, with this many eyes in the sky, your data, which may contain everything someone may wish to know about you, is out there on the internet, increasingly beaming between communication satellites. That information is also valuable to has launched nearly 7,000 satellites into space. Oh, and one Tesla Roadster. As it stands, SpaceX have twice as many active satellites in low Earth orbit as every other company and country on the Earth combined. I've seen some hockey stick shaped graphs in my time, but this one is stratospheric. The vast majority of these new satellites have gone into low Earth orbit at an altitude of only 550 kilometers. The United Nations Office for Outer Space Affairs have speculated that 100,000 more satellites could be launched in the next decade. There are no regulations that limit the number of satellites that can be launched, and many agreements and understandings around reducing the potential for light pollution are informal. These satellites in low Earth orbit are particularly bad for light pollution, contributing to sky glow and producing trails in amateur photography and research images that can render them unusable. Astrophotography can require long exposures of several minutes, and it's likely that these exposures will capture the trails of satellites in that time. This is an image of the Horsehead Nebula, and there are 3 trails in this image. And even I myself have seen it in my own shot of the Orion Nebula. We can easily see the effect satellites have on visual astronomy. We can even watch them trail across the sky in real time. But these man-made constellations that deliver GPS, mobile communications, and satellite internet all operate in the radio spectrum too, spanning megahertz and gigahertz frequencies, which can potentially interfere with scientific observations. Radio signals easily pass through galaxies, solar systems, interstellar gas clouds, and Earth's atmosphere, revealing secrets of our universe that would otherwise be hidden. All the more incredible then that the radio signals from my Wi-Fi router can barely make it through a few stud walls. But radio astronomy was key in establishing the shape and rotation of the Milky Way, discovering quasars and pulsars, and detecting organic molecular species like cyanide, ammonia, water, and amino acids in interstellar molecular gas clouds. It was a radio telescope in Ohio that received the famous WOW signal in 1977. It was detected at 1420 megahertz, a value believed to be the frequency of choice that an alien civilization would attempt to communicate over, and it is protected from commercial use to keep it quiet. It is though still debated whether the WOW signal was terrestrial interference or an extraterrestrial phenomenon. But while we are talking about how communications interfere with astronomy, astronomy can also interfere with communications. In 1978, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics for discovering that the interference in their antenna wasn't pigeons, it was the cosmic microwave background, the cooled remnants of the universe's first light. The detection of this low-level hum in their Bell Labs antenna and understanding its cause all but proved the Big Bang hypothesis. In another happy accident, the radio waves emitted by the black hole at the center of our galaxy, Sagittarius A star, were detected because of its interference with transoceanic phone calls. I love these two stories as it highlights humanity at its best, at its most inventive, and at its most curious. Pausing in the hustle of developing new technologies to remark, that's odd, led to two incredible discoveries. So much has been discovered in the radio wave spectrum, yet there are deeper mysteries that cannot go unsolved. That's why the Square Kilometre Array Observatory is being built in radio quiet zones, the most ambitious radio observatory project of all time. I don't say that lightly, it is. Its stated aims are to probe the cosmic dawn and the emergence of the first stars and galaxies, to challenge Einstein's general theory by indirectly observing gravitational waves, to seek the origin of life, to look for aliens, and to understand how our galaxy and universe are changing due to pressures like entropy, gravity, and dark energy. But what does that change look like to us from Earth? If we look up to the stars through a polluted sky, space appears stagnant, and it can be easier to believe that we are instead on a Truman Show-like film set with fixed stage lights for stars than on a rock in motion through our galaxy. But under a dark sky, nothing feels still as we get a sense of our voyage through space and time. Earth is orbiting the black hole at the center of our galaxy at 828,000 kilometers per hour. We are heading away from the galactic plane and hurtling in towards the center. Our perspective and every object we can see is moving. In this video by ESA, from data captured by the Gaia telescope, we can see how our night sky really is changing. In 1,000 years' time, only the keenest astronomers would notice a difference from today's constellations, though we may be lucky enough to witness Betelgeuse going supernova. But in around 10,000 years, we will have a new North Star. Polaris will have moved away from the celestial pole, and it will have been replaced by the brighter Vega. And let's take a closer look at the constellation of Orion and the stars around it. They will change dramatically over the next 450,000 years. Orion's sword will shatter and his bow will disintegrate. Zooming out to the entire night sky, let's watch our galaxy evolve over 4.5 million years. Orion is in the bottom right. What we can't know with this data though are how many more stars will go supernova and how many more will be born. We'll just have to wait and see. And that's going to be a heck of a lot easier if you would just turn off those up lights. But over the next few billion years, the sky will begin to look so unrecognizable that you would be forgiven for thinking we were in a different galaxy altogether. Because we would be. Andromeda currently takes up 3 degrees of our sky, about 6 moon widths. It is accelerating towards us and is expected to reach us in 5 billion years, by which point it will be the sky. Galaxies are so diffuse that Andromeda and the Milky Way would pass through each other almost without impact. But it's what we can't see that is all around us that will seal our fate: gravity. Over the next 5 to 10 billion years, our two galaxies will yo-yo and rip each other apart with a huge burst of star formation from the mixing gases, turning two spiral galaxies into one elliptical blob. Unfortunately, you would be unlikely to see this from Earth because of the extreme natural light pollution caused by the sky literally being on fire. Our sun will have become a red giant. In 1 trillion years, the last star will be born. There is nothing but decay left for the universe. The galaxies we can see outside of our extended galaxy will become faint and dim as they move beyond our observable universe. In 120 trillion years, all stars will be extinguished and the night sky will fade to black. As is so often the case in our complex world, there are unexpected outcomes from our behaviors. Our night sky is changing in many ways. It has been obscured, but it is not lost. Towns, cities, and governments all over the world are beginning to understand the issues and are making changes in ordinances and in law to protect our skies and the wildlife underneath it. So,